All right.
I'm doing good. I posted up. Well, I've gone through. Oh my God. I'm so sorry. I actually did this screenshot email thing, but I've made a matrix, which I have now. And so I've gotten everybody, as far as all the screenshots I found in my email, are all in the grade book. So if you're missing anything or something like that, that means either A, I didn't get the email, or B, my old butt missed it somehow. But
I'm still
um
submitting my screenshots for my labs.
huh?
I said I'm still submitting my screenshots for my labs.
Okay. But yeah, like I said, if you go through your grade book and it looks like there's something missing or something like that, just get with me and show me. I mean, we can do it any which way. It's if you have the copy of your email and resend it to me or whatnot, or you know what I mean. For whatever reason, I don't know. Email sometimes it bounces and crap, um, but yeah, everything should be all up to date and graded, I guess, at this point, if you will. If anything looks like it's an error, get with me on that as well. I did post a bunch of new stuff. I was gonna, I was going to do like a differential like homework, but the lab I posted for it I thought was a lot more extensive with the formulas and whatnot. So I went through it really well, and I hope. Of course, I don't know. Sometimes my labs have a little bit to be desired, and I know you'll agree with me. I know. But let me go through here real quick and pull this up just to go over it real quick with you guys. If I can get this screen share thing to work properly. Uh, I can't remember here. All right. Well, yeah, I mean, it should be fairly straightforward, doing a differential amplifier. And I think I did this fairly well, so it shouldn't be too complicated what you're actually looking at. Remember when we talk about like when it says VC1 and VC2, referring to basically taking your collector voltage readings here. Now, remember the only reason I found that this was like somewhat important, it's like, okay, we covered, and that's what I didn't like about the Frenzel text, all right, because the op amp incorporates both this amplifier and the like class B power amplifier, if you will. It's sort of like a way to look at the op amp is like a hybrid of the two amplifiers together, right? And Frenzel doesn't, and the way he did it, like, he did chapter 37 was where he got into power amplifiers, and I was like, why in the hell are you talking about these after you've already gone through two chapters of op amps? So that's why I jumped ahead on that, and now we're going back to chapter 30. But again, you should have had this as an intro into operational amplifiers too, just to understand what's behind the whole thing, why we're getting the readings and whatnot that we are. um but yeah, if you guys have any questions on this, it's really simple table, two questions, asking about common mode rejection ratio, and then and a trick question about the collector resistors and why they're balanced like they are, and what would happen if they were different values. And that's kind of an Ohm's law kind of approach, if you will. So I know, and it's a little analytical, but it should be fairly straightforward. I went through it fairly well, and really you only have a couple readings to actually list out. But if you have any trouble with that, let me know, and then I will. Do you guys still want me to do like the video demonstrations, if you will?
Yeah.
Yeah, that does help. All right, let me look at something else here then. Don't worry, I do have a lecture today. We're gonna we're still looking at op amps. We're going to be looking at op amps for a little while now. I'm going to warn you guys. Op amps are what we're headed to. I had a, trying to think. Oh, I'll sort through that later, but so yeah, we'll go through today. I'd like to look at op amps again, a little differently, if you will. We're gonna take a look at Malvino, what he has to say about this, and point out a couple of our golden rules, if you will. Here. Share. Sure, I got everybody in. Chat. Gotta check chat. Did you work at Circuit City? You know, I bought my no, I'm sorry, I digress, but I bought my very first Pentium computer I got from Circuit City, believe it or not. I was really proud of it. It was almost $1,000 for the damn thing. I had a 1 gigabyte hard drive on it, which I thought was so awesomely huge at that time. You know, my very first, you're gonna laugh. My very first computer did not have a hard drive with it. It actually had two 360K floppy drives. Yeah, 360K. Okay, and then and they eventually went up to the high density ones, right? But at that time, I didn't have that, so I had two 360Ks, and then the little 3.5-inch diskettes, if you will. They were like the plastic coated floppies, and I bought one of those, and that was a 720K, and I was like, woo, the room on that bad boy. Yeah, when I was and then when I was going to school, they'd step them up, and they came out with the high density versions where it used both sides of those discs. Because the original ones only had a one needle, basically, right? The swing arm that read only one side of those discs, so the back side was literally unused. So what they did was they came out with the dual sweep where you had arms on both sides, right? And so of course now it's double densities on these things. So they went up to I think it was like 1.2K on the big 5.25 squares, the terrible ones, and then it was I think it was 1.44. I mean megs, 1.44 megs on the 3.5-inch like hard coated ones. I went around and of course this was like a bootleg copy at the time, but I had 10 of those 3.5-inch discs where I had the Doom game on. And yeah, you had to literally, while you were playing the game, it would pause. So you had to keep, please insert disc 6. And it's like, oh my God. And then finally I bought a hard drive. And you might laugh, but it was a 20 megabyte hard drive at the time. Yeah, it was whopping huge. And it made noise. It was huge and heavy as hell. And it was, when it would run, it'd be like, the whole arm swinging through. And yeah, when I first started work out in California, they had it was just getting downgrade. Yeah, Doom and Duke Nukem was awesome. I played that when I got out in California. I had a better system by then, but I had the 486 at that time with a much bigger hard drive. But oh yeah, when I was working, they were just phasing out this one system, but it had a 750 megabyte hard drive on it. I don't know if I told you guys this, but this thing had to be put into the machine with a forklift. Yeah, you couldn't lift this hard drive by hand. 750 megs, and it was about pallet sized, roughly. Yeah, it was humongous. The platters on this thing were huge. Like you could kill somebody with one of the platters in this thing. And it had like literally a whole stack of these platters. But yeah, you couldn't lift it by hand. You had to have the forklift come in and literally ease the thing into the bay where these things were in. So once these things went in, they didn't come out, not without you know, the boom tackle, like I'm powerlifting here. it was, once it was on a trade, that was it. It was done. But yeah, 750 megabyte hard drive, and it was humongous. And then we phased that out, and we're going with the new style systems. And yeah, we had the at the time they were actually so nice. It was on SCSI. They were like 2 gigabyte, 4 gigabyte hard drives we started putting in, you know, the regular. They were still pretty big by today's standards, but if I compared to that thing, it was nothing. But yeah, I got to see a lot of interesting changes, if you will. No one remembers the Triad. Well, I remember Duke Nukem. I like Doom a lot. I like Quake when that came out. A lot of people didn't care for Quake, but I don't know. I thought it was pretty good. Anyway, Rise of the Triad. Well, can't help you there, Ryan. I don't know what Rise of the Triad. I'm trying to think. Maybe if I seen it. I got into what did we play back out? Well, we played Duke Nukem a lot at work. You know, during our breaks, we had all the office computers. We had Quake on them and Duke Nukem, where we could play multiplayer against each other, kind of thing. And then around that time, Warcraft 2 came out, which was was pretty. Yeah, it was kind of on the break. Break sometimes got a little long. So yeah, okay, op amps. Enough of this. I digress. So, you guys see my screen, right? Yeah, right. Introduction. All right, good. So we look at a few things here, right? I will post up Malvino's chapter 16 if you need to read through. Use it for like a reference. I always feel it's he gives a clear presentation than Frenzel does, right? So we're really looking at, and they had knockoff versions of the 741, but 741 was a pretty standard op amp, and you can get it in a variety of styles. If you go look on the spec sheet, you'll see they have literally from SOICs, which are like the surface mount style, right, up to the through hole ones with the dip style, right, dual inline package dip, where it's got the teeth where you plug it in kind of thing. They have that, the plastic coated style. Then they got the can style where it's literally the metal ones, and you know, that one's the workhorse, right? So you expect a lot of heat where it's made to be mounted on heat sinks and whatnot. So it's got a lot of ranges to it. It can do quite a bit. And the thing to always remember with these things, these are like the golden rules, see? And like I said, and see on the bottom one here, right? See how we got a differential amplifier in the beginning, and then out on the end there is a push-pull amplifier, right? Class B power amplifier right there with the differential amplifier as the input. And so with that, we look at it and say, okay, we got a high Z differential input. I mean, in an ideal world, it would almost be infinite, literally, and that's why you can call it like a virtual ground point, right? And then on the output, a very low impedance, which kind of sets us up, which is why we like to use operational amplifiers so much, okay? So here's our classic symbol for it. This is in the ideal world. We only use 3 of the pins, and it's an 8-pin IC, but ideally we only look at the 3, where we have, whenever you see the plus sign, always think in your head, non-inverting, minus sign is inverting, and this is our output. And these are the ways we would look at it. We have, in an ideal world, we got a high impedance where it would be almost infinite, a high gain where, and that too would, in an ideal world, would be infinite, and a very low impedance output. So let's look at some of the insides of this little bad boy. So just like in our transistor models, right, you notice that we like to use VCC and BEE. So we have a plus, excuse me, a plus DC supply, and we got a negative DC supply on this guy, right? And what that does when you basically what that does is it sets you up, and I mean, in an ideal world, yeah, you got infinite gain. In reality, nah, it doesn't work that way. Nothing ever does, right? But so your positive and negative supply are basically what limits your range of what your voltage output could be. So the higher they are, right, the better, the more range you would have on your output. But you have to take that with a grain of salt. You know, the more range you give yourself, the more problems you end up giving yourself typically too. But, oh, there we go. Admit. But the way you would look at that, and this is a very classic, I mean, we'll play around with this formula a little more for you, but so straight out, if we said, okay, what's our voltage output? And this is just looking at the amplifier without a feedback loop, you know, closed loop or open loop gain, anything like that, right? This is be considered an open loop where I am not tying a resistor in from the output to the input. Okay, there's no what they would call a feedback resistor. And that creates a loop, right? Because you would literally be looping from the output to the input. So if I don't do that, then we look at it and say, okay, it's an open loop because there's nothing there for feedback. Now, this opens up a fair degree of an ability to basically create more distortion, if you will, when we go to the open loop, but we'll examine that a little later. So yeah, just looking straight at this model, and then we look at, okay, our two inputs are tied in with the RN, right? And then we look at what we have coming out, where we have a AC source hitting your resistor and cranking out the voltage out. And the way we would come up with our formula model, and this ties in with, because you know, you have to think, both of these are inputs to this thing. And even if you ground one out, it's still technically an input for this. And granted, it would be a 0 volt reading, but it still plays into the formulas for this thing. So you can't disregard this. And that sets us up for right here. All right. So on the left side, we see in a perfect world, this is how the op amp would work, right? And on the right side, this is reality. And granted, reality is still pretty damn good. If we look at our ideal, our voltage gain, like I say, would be infinite, right? We'd be able to crank it out all day long. In reality, our voltage gain is, it could be up to 100,000, can be up to. That doesn't mean that this thing's always going to be that. We would just be, well, we'll get into what limits that in a little bit here, but our bandwidth would be infinite. In reality, no. But we do have a very large bandwidth, a 1 megahertz swing. So if we were to look at the Bode plot, we would have like an upper and lower limit that's pretty decent, right? And we can examine that by our common mode rejection ratio, which again, an ideal world would be infinite, but in reality, we got a 90 decibel swing on this thing. Now, if you remember from the earlier, when we were looking at like the small signal amplifiers or even the power amplifiers, if you will, we did not get a 90 decibel swing, right? As ours, for our upper and lower limits for our bandwidth. No. But so we've got a very large range with this thing. And then, like I said, in reality, you know, we don't have an infinite resistance, you know, as the input, which would be our virtual ground. But we do have a very large number here, 2 megohms, which is an extremely large point. Your typical scope probe, I think, is usually comes in somewhere around 5 megohms. So 2 megohms when you're dealing with like K resistors is very large. And we can treat that as almost like a virtual ground point, if you will. and so this just gives us our realities. It's like, okay, what do we have? And our slew rate, of course, would also be infinite, right? But in reality, let me see here. The window's in the way. Yeah, so we have a slew rate of half a volt for every microsecond, which is, again, compared to our earlier amplifier models, it's actually quite extreme. And that's why these things are as popular as they are. And so we look at a graph to try to get a bit of an idea here. And now you notice, okay, so we said 90 decibel range on this thing. So what does that give us, right? So if we look, see how we look at this? So we literally look at our lower to our upper limits, and we can run all these frequencies through this thing without experiencing distortion. Okay, that's the deal that we're getting out of this. Whereas before, you look at it like especially the small signal amplifiers, we had a fairly narrow range on that thing, right? You know, we tried to exceed it or go under it, we'll start getting a major amount of distortion. But in this case, excuse me, we don't have that. We have literally, I mean, this is huge. Huh. And so we do our comparison, right? Our gain to our bandwidth, and I mean, again, the amount we have here is just insane. How much we can get out of this thing, and with very little in the way of componentry as well, right? So we're literally plugging this guy in, and depending on how we set up our resistance values and whatnot, that's pretty much it for as far as our inputs to our outputs go. I mean, look at how many components here. We have to have 2 supplies. We have, and it's pins 1 and 5, they deal. I talked a little bit about that before with the Frenzel and the Frenzel presentation, but what they're looking at is basically you're trying to adjust for feedback, if you will. And so you would basically set this up as, see how the circuit's set up where you literally have no inputs going in. They're both grounded out with resistors for any ground bounce, right? So that way you're ideally getting 0 volts. And so what you're doing is setting this thing to have the minimal amount of you would kind of experiencing, if you were to like monitor what the voltage output of this is while you have these grounded out, you might, if you, and you'd have to do this on a scope, right? A voltmeter wouldn't cut it really, but you could, yeah, I mean, you could still see the amplitude with a very nice voltmeter. But to really see what you're doing, an O-scope would be the best way to go with this thing. And then you would notice almost like a little ripple, and there might be a slight DC margin. So what you would do with this offset null is you're literally setting like the 0 baseline for the output. So it's at the ideal point. And that's why they have that. And if you look at the spec sheet, it'll even tell you, it'll have this pretty much this exact model and tell you what range your potentiometer should be and what your VCC and VE are set at that point. Yeah, so see how it says adjust R1 so that V out is equal to 0 volts. And that's really what you're doing. When you look at it, when it's like an untuned mode, you will see probably a marginal like DC offset, DC shift. And so we look at our slew rate and how fast. And what this is it's like a reaction time, okay? How fast can this thing handle a transition? And so, and we want that because essentially, I mean, if we were just settling in like a DC signal, you know, where there's no change, who cares? But we're not. We're going to be sending it in. And a lot of times, especially with like audio and whatnot, your frequency shifts that'll happen on these like audio signals, it changes literally as it goes along, okay? If you were to monitor it on an O-scope, you would think, okay, sort of sinusoidal, but amplitude changes and your frequency response is changing as well. So it would be swinging in and out. So what you're looking for is something that can react to that as well. And so that's what we're looking at when we talk about slew rate. It's like, how fast of a signal can this thing keep up with without causing some distortion? And that's really what we're setting here. So a half a volt per microsecond is actually fairly fast, right? If we were to look at what the frequency would, you know, we'd have to just basically swing that micro. So that would be up in what, the megahertz, micro up to the top. So you're looking at, you know, from hertz to megahertz change here, which is pretty ideal for most applications. Of course, and now we get into this day and age where now our frequencies have gone up much higher. Now, of course, we have like newer op amps that have even faster slew rates, if you will. But then you lose out on the lower bandwidth with those types. So these types are designed more to operate in the upper ranges. But still, same principle. You still got a wide swing on it. Now you're just setting, instead of like this one, right, where you can go down you know, practically to 10 hertz here, our swing would start out something like this and travel up higher, if that makes any sense. But so yeah, so you'd be looking at typically in comparison, right? And it's like, how fast can this thing handle? And it's like, well, we can do pretty well actually for our slew rate. And notice you're not really experiencing any distortion on the outputs is what you would want to see. So if we actually tried running up, like say if we, because based on this, so if we had 1 megahertz as our upper range and we tried cranking in a gigahertz signal, if you will, right, something really fast, yeah, we wouldn't be looking at this nice, smooth, pretty output. It would look a little crazy, a lot of distortion to it, that kind of thing. But essentially, that's what you want. You want to experience no clipping, right? And you don't want any distortion on the rise or the run of this thing at all here, if that makes sense, right? Because some cases you might have like a frequency response where it would affect along here, or we could get the clipping where we affect the amplitude of the signal, if you will. But here we reproduce a signal, nice, clean, smooth. Okay, so we get into one of the types, and essentially we're going to deal with our first ones really are going to be the inverting amplifier and the non-inverting amplifier. And what does that mean? Well, for the inverting, what we end up doing is we tie the non-inverting input to ground, and then we apply a signal into the inverting side. And we notice we have 2 resistors in this case, right? You have the input one, in this case designated R1, and you have a feedback loop resistor. See how the feedback loop resistor one is tied in like that? So here's the output literally tied back to the input, and that's what they call the closed loop, okay? Right through there. And so some of the things we need to know. So if you notice the very first one we're dealing with, it's an Ohm's law, right? So we have our voltage input, which is this guy. And then we have our current, and we have our resistance value right here, straight Ohm's law. And we look at our output. And because we're going into this inverting, this minus sign, see how we add that in? So our output would be considered a negative, which would mean to us what? That our AC signal is literally flipping 180 degrees, right? That would be an inverted output, if you will. And then we look at, okay, how do we arrive at a formula for our overall gain? And again, transfer function for these things is always your voltage out compared to your voltage in. It's just how you arrive at that. Well, in this particular case, what are we going to look at, right? We set what our voltage out is and we set what our voltage in, and we end up dividing those two out, and we come up with this little golden rule. And this is always the case where the AB of an inverting amplifier is always equal to minus RF to RI, right? So your feedback to your input resistor ratio, inverted. So depending on what your resistor values are, that'll determine what your AB of the circuit is going to be. So if we plug in some numbers with this thing and we have like a 10K feedback resistor and we have a 1K input resistor, right? We set our voltage out and we're going through and plug this through. We have a 1 volt input, and we come out with our what would our overall gain factor be in this case, right? So we have a gain of 10 or negative 10, if you will. And so if we have a 1 volt in, we expect to get a negative 10 out. And what I mean by negative, you know, and you can't, okay, we had an AC signal. How do you have a negative AC signal? Well, it would be your output is literally shifted, I mean, by 180 degrees. So that's what you would expect to see if you were probing with a no scope onto this. All right. And again, that's a golden rule with these guys, that our gain is always with the inverting one. Now the non-inverting is a little different, but the inverting one is always a minus RF over RI as our values. And then of course, let's forget all that. Now we'll go on to the non-inverting amplifier. Now notice, if you will, that we still tie the feedback loop into the inverting side, right? If we look at the first model here, we have the feedback loop on the inverting side. And a non-inverting one, we do that as well. We just don't have an input coming into this side. We are literally applying our AC signal into the non-inverting input, if you will. But the feedback loop is always tied in with this. So we still have to do our Ohm's law derivation. And so how does our gain come out for this guy? Well, it's slightly different. And the reason being, of course, is the way the feedback loop is tied in and what our path is to ground here, right? So another golden rule that for a non-inverting amplifier, our AB is always going to be equal to 1 plus RF over RI. So the values we select for these resistors become extremely important to how we're setting the gain for these amplifiers. And he makes a special note here that we have this virtual short. And so I'm going to point out now, when I talk about virtual ground, what I'm talking about is the ground potential between these two pins here is literally that 2 meg reading. That's what this is. So there is literally a virtual ground established at this point. And then another golden rule we're going to come up to is that this E plus equals and follows E minus. And this is a very specific thing to op amps, and you always have to think of it in that way. And it's not the other way around, but E plus equals and follows E minus. And I'm just going to let that sink in a little bit. We'll get into that. But let's examine this. Now we'll throw some values on this guy. And notice our gain factor, even with the same resistance values that we had for the inverting style, our gain factor in this is 11 compared to a 10. And we're positive. So we'll be matching phases up here. So if we're putting an AC sinusoidal in this way, it'll be in the same phase, no phase loss, right? Going through this thing. And we have a little summing circuit, if you will, where you would have two different voltages coming in. And if you remember, now think about this. We have this virtual ground point being established here from E plus to E minus, okay? And that changes how we can look at these things. So if I were to say there's a ground point right here, okay, then we can look at all three of those resistors, just like it says here, as being in parallel. And because of that ground potential being established like that, that would establish what our value is here for R3. Because of all that, that's because of this virtual ground point between these two pins. So when we do this simulator model, now remember this thing's going to be ideal. Actually, that's actually a great thing, really. So you'd be able to treat it as such. And the only thing that we'll be going into when we do these labs for the op amps, we'll have to be setting what our voltage inputs are. So VEE and VCC, and what those values are settable on the op amp device. So we go and plug through. We got a summing one, right? And we're tying into the inverting input. So we're dealing with our gain formula where we have to have RF over RI, right? So if we do that, we say, okay, in this case, if everyone could see that well, right? So we have our closed loop gains, and we treat it as two separate ones because we're gonna have two separate voltages here. So I look at the closed loop gain of the voltage input 1, and then I look at the closed loop gain of voltage input 2, where I'm going to set this RF, the feedback resistor, is going to be over R1, and then this one's going to be over R2. And then we go ahead and sum up the two, and that's why they call it the summing amplifier. You're literally summing those two together like that. See how he does that? So what we end up with, we get our voltage out, and because we're tied into the inverting input, it's going to basically throw it out of swing by 180 degrees, right? So we just establish a minus sign to that, and it should come out as a very simple formula. Just establish each leg at a time, and boom, boom, and that should be your voltage output. And so as you vary your changes, you know, depending on what you have going into V1, what you have going into V2, I mean, your resistant values are going to be fixed, so you could even come up with a ratio in this case, and then for each voltage change, it would just change what your voltage output is. And then throw some numbers in there just to see how well does this work. And it's like, okay, let's do that. And so it literally sums up, okay, so we have 100 millivolts in on B1, we have 200 millivolts in on B2. We go and plug it into our formula here, right? So in each case, we're going to multiply those by a factor of 10, right? And see how we arrive at this? And get our voltage output. I hear nothing. Oh, it hurts. It hurts. No, ah, ah. So we go along and figure out what our R3 value is right here, right? Oh, silence means yes. Okay, that's what I always say. Silence means yes. It's a joy being a teacher sometimes. Anyway, so going back to our original formula, like, okay, how do we determine what our value of R3 is by our fixed values here? So we'll go through and plug those in and treat them all as if they're in parallel. And we do this with our classic formula, right? 1 over R1, 1 over R2, 1 over RF. Boom, boom, boom. Do the math and come out. Okay, we get 625 ohms. And that would establish that. And that's based on what we have as far as our input ones, which ones we designed with or which ones we selected, if you will. And then we get a real easy one for you. You'll love this lab. It's so simple. You get the voltage follower. Now, and I've talked a little bit about this, and why would you want to do a circuit like this? Where if we even do the math, okay, all right, if I say, all right, what's my math? We're using the non-inverting input. So if we said, okay, our gain is equal to 1 plus RF over RI. So what's our RF value in this case? Ideally, it's 0. And what's our RI or R1 input is 0. So what's our gain end up being by the math? It's 1, right? So we literally have a gain of 1. And now, why would you want to do something like that? What would be the purpose? Oh, a good reason that they use something like this is as like a noise filter. Let's say you had a signal that you were getting in that had a slight distortion to it. I mean, overall, you could still follow the sinusoidals, but you did have a little bit of distortion. What this signal would do, I mean, what this circuit would do, it would take that noisy input and literally create a nice, smooth output without changing the amplitude or anything of the original signal. And it would follow it through, you know, like in an audio mixer type of case or whatnot, right? And you could get a certain amount of distortion to it. It would follow it through frequency-wise and amplitude-wise and generate out a nice, smooth signal for you. And that's generally why they use a circuit like this with the voltage follower and set up something that they call unity gain. They also use, you'll see this in the spec sheets as well, where they do have a unity gain circuit. And this would be to determine the overall performance of your op amp, if you will. Kind of like a tuning circuit to see how well this thing will perform with like given frequencies or given amplitudes, if you will. So what I would be doing is like setting up and deciding, it's like, okay, I'm going to be running these kind of frequencies. Let's see what the response overall is and that kind of thing, what kind of heat I generate out, whatnot. And that's when you would set up a circuit like this to kind of test the device, if you will. But yeah, I mean, in an ideal world, right? Your closed loop gain is 1, and your impedance literally is infinite. Well, 2 megs, right? And your output in the real world would be 0. You would have 0 impedance on the output. Well, reality never works out quite that way, but it comes fairly close. And we're dealing with, so in this chapter, well, in this chapter and then in Frenzel's beginning chapter here too, we're dealing with linear applications, if you will, and what kind of things we would expect to use these with, right? So if we looked at audio amplifiers like a low noise preamp, right, we expect power range to be anywhere from 0 to 50 milliwatts, pretty low all in all. Small plastic package sizes, not much heat. So you can find that in the front end of audio receivers. All right, they'll be taking in signals. And then we look at medium level amplifiers where we're getting a little higher up in power, right? 50 to 500 milliwatts, a little more heat and whatnot. Not too bad. You can still probably deal with a plastic SOICs or even the dip styles. And where do you find these? Yep, cell phones, MP3 players, any low end type of radio signals, if you will. And then you get into power amps where you actually will now be putting in some serious signaling. And that would be 500 milliwatts or greater. And these styles generally change. If you look at the spec sheet, you'll see there's actually a can style, right, where it's a steel package. It's meant to be mounted on a heat sink of some sort. Big giant ones, depending if you're generating out a lot of heat, or small ones if it's minimal. But yeah, you'll find those in actual like intercoms or radios, stereos, or anything like that, where you're going to be pushing it a little bit, if you will. And yeah, and these kind of basically all the linear applications we'll be doing, like these types of circuits, which are those the comparator, the non-inverting, inverting amplifiers, the summing. These are all linear applications of the op amp. And then later on, we'll be getting into other applications and doing other types of circuits, and that's considered non-linear. So we can expect an ideal response, linear, nice and smooth. And these are the type of thing that they would do with them: video amplifiers, RF amplifiers, IF amplifiers, pretty much a lot of stuff that you run into in your day-to-day thing. But yep, these will be at the heart of all of that. And then, like I said, this is like more of a clarification on Frenzel's approach. I felt it was a little simpler. And I mean, one of the things to really remember with these guys is what we're dealing with here. And we'll be getting into our golden rules. And like I say, our voltage gains. So the voltage gains for both types you would want to remember. That would be like a takeaway for this thing. Another thing to remember is the way our inputs deal with each other, that E plus is always equal and follows E minus. So the way you deal with that, I mean, the voltage potential here is going to be the voltage potential here, but it follows, right? So if E plus equals and follows E minus, that means he's first, always and foremost, and then he's next, if that makes any sense. Another point to always remember is that the potential points between these two is an infinite, right, input. You got a high impedance factor, ideally infinite, but reality usually up into mega ohms. And then, like I say, the gain formulas with these guys. And then another thing to remember will be our current potential, where I plus is equal to I minus, which is always, 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 because here's a trade-off if we do Ohm's law with this thing, right? If I had, and the voltage can vary, okay, but if I had an infinite resistance or an infinite impedance, what do you suppose happens to my current? Just for grins and giggles. Well, usually you have some kind of trade-off that happens in the case, right? So if we have an infinite resistance here, we're literally going to have big fat zero of current. So your I plus, I minus equals, right? And it always, 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 always equals zero, always. So if you went and tried to put in line and get a current reading out of these things, you're not going to see anything. So you'll vary voltages on this thing. Your impedance will not change. If it does, I mean, you're pretty much somehow exceeded this op amp and blown it, but it's fairly hard to do. It does happen though, but yeah, that's one of the trade-offs with these guys. It's got because of that high impedance, you literally have no current going on here. Literally, I plus equals I minus, which is equal to zero. So that would be my takeaways with this. That E plus equals and follows E minus. I plus equals I minus equals 0. And potential impedance between these two is always, always, always extremely high. And then basically the two gain formulas for the types here, and that should set us up for what we're going to be dealing with as far as operational amplifiers. And then after that, everything else is, and you guys are going to hate me, but everything mostly what we're going to do is, it's going to be Ohm's law and like KVL. I'm not going to get real crazy or anything with any of the math in this. I mean, again, this is all straight, right? Parallel formulas. And just got to be able to look at how these things deal with it and why. So if we establish that, like I say, that virtual ground point at this, you got to like, and of course it's not going to be drawn in there for you. You got to mentally picture that there is literally a ground point established right here. Okay. And then deal with it from that point and go, okay, so if I do put a ground point here and kind of, I mean, if you need to redraw the circuit, okay, and put the resistors in line like that and go, oh, okay, so these are, and that's why these end up being in parallel like that, is because of that ground point right there. And so that's something to always remember as we start dealing with these op amps, for like our circuit application from a design standpoint, if you will. But, and that's pretty much my lecture for today. We'll go through, I got the homework all posted up, and I'll be going through some more labs, if you will. And these beginning ones with the op amps, they won't be really complicated. There's, I think in the non-inverting one, I just ask you to go through and change like the feedback resistor value and step it up and just observe what happens to each one, because that'll change the gain factor, right? And the same with the inverting one as well. So I'm gonna have like a couple of op amp beginning circuits for you. So if you have any trouble with any of those, let me know, and then we can go through them, and hopefully it all comes out fairly well. So do we have any questions? You guys need me to model through any of these labs while we're all together, or I'm gonna stop sharing that. Here we go with the silence again. Ugh. See, this is what I hate. I don't like being in class, because in class you guys will pipe up, but no, not in here. I'm not going to talk. No.
I'm good. I mean, if anybody else has questions, but
I mean, we're going to go nice and easy into this. We're going to, see some of the applications that we do with the op amps. And then as we go along, once we start getting used to the rules, right? We always got to know our rules. And again, we're only really, we're just looking at the device, and then really we'll be applying Ohm's law and KVL to it, and just coming out with, that'll be the most complicated. And I know some of them actually do end up kind of complicated when you look at how is our KVL approach, but it shouldn't be horrible. I hope. But like I said,
after recording.
No, that means it's going to be about when are the labs due? Good question. You know what I did? I haven't made a due date on these because I've been having so much complication with everybody wanting me to extend the dates and stuff. So I kind of left them open, which I know was asking for trouble, but no, as far as the due dates, we're going to keep it, get out of here, dog. We're going to keep it pretty open. I would like you to do them as soon as possible, because I feel that the labs, I try to have them follow along with the coursework. So if you end up falling behind, you're not getting the interpretations that you should be. Yes, I see you, dog. But, so yeah, is it still okay to send snapshots? Yes, I would like to see that you've actually set the lab up. It would be kind of like the proof, if you will, that you're still setting these labs up, because otherwise you're just answering the questions. Although I'm going to start getting more complicated. I think I'm going to start asking for when we're taking voltage readings and stuff in the tables, I'm going to start asking you to input those on as well. So if you're trying to just make up numbers and stuff, then I'm going to look and go, oh no, there's no way in hell. But so yeah, I just want to make sure everybody's actually doing it and learning how these amplifiers work and stuff like that. If that's okay with all of you. I mean, I don't want to make it extremely hard. I just want, everybody getting their learning. You got to get your learning. Does that sound fair? Oh, I'm getting mauled by my dog. Oh, dog.
Sounds good to me.
All right.
Hey Tom, in regards to the readings, so the readings that show up on the circuit board pop up, but the graphs don't, like the oscilloscope. I just wanted to make sure you were aware of that, since I'm not seeing those in my screen caps.
What do you mean
So when you take a screen cap in every circuit, it's only capturing the circuit.
Oh,
It's not
yeah, I
capturing the
know. You
oscilloscope.
can't actually see the waveforms. I know.
Yeah.
Yeah, and that's why I was kind of thinking of doing it where, like, because like in well, you'll see in some of these where I'm just asking what your voltage output readings are. So I'm going to start asking. I'll have the questions still. They'll be 1 to 4 questions, but then I might have you start inputting like the various voltages or that kind of thing. Because you can still see, I mean, as far as even in sinusoidals, you can see what your voltage peaks are and what the frequencies are and that kind of thing.
Yeah.
So yeah, so I'll be asking basically as I keep going through these labs. I hope, give me feedback on these next few ones, especially like 9 and 10. I have to think about that, but that I did, that hopefully they're very straightforward and much more applicable to the simulator. So that way it's not as frustrating for you guys. So today I'll go through and start posting up some video demonstrations, I guess, for the circuits, because I've been going through, and then I gotta make sure I save these privately, because the electronics community out there is hazing me a little. I was like, oh my God. Anyway. But yeah, no, I know you can't see waveforms, so that's a pain in the, and that would be nice, right? Because ideally that would be the proof of the pudding that your circuit's working correctly. You got the proper response back out of it. But yeah, as long as you show me that it's built, I mean, then after that, because I don't want to have to go through, because I don't know, it would be tedious. But if we had to go through like this Zoom software and then have you share your screen with me each and every time would be.
That'd be awful.
Yeah, that's what I'm thinking, right? It would be painful and awful, right? I mean, I wouldn't want to have to do that. I wish there was a way we could actually get the outputs with that, where it would take like a snapshot of the output or something like that as well. But I know. So, but yeah, let's still send the snapshots through email now that I got my proper matrix going, and I'll wade through this easier. But yeah, I tell you, I've never had so much email. It's almost worse than spam email. No, yeah, quite a bit of email. But yeah, let's still do that. Answer the questions, and like I say, I'll probably be asking, like for certain ones, like the values, like what the voltages are, that kind of thing, and enter those in on Blackboard as I get more online oriented here. So I apologize. I know none of us were quite ready for all of this. But So no other questions? You guys are good. But yeah, like I say, go through these, let's go through these labs. I got all the questions posted up to the ones up to date, and then let me know what you think of all of it, if it's horribly painful or if it's okay, that kind of thing. Don't be shy with me. And then, oh, and that's one other thing. I got can't remember. I guess we'll have to do a quiz for chapter 35 coming up as well, right?
Yeah, that's on Friday. Or this 37 one is on
Well, I had the
Friday.
chapter 37 quiz, but now we're gonna have to have a chapter 35 quiz after that. So I'll be looking for it. I'm not sure when I'll post that up, but yeah, we'll have that coming up too for chapter 35, going into op amps. And then we'll get through, like I say, we'll get through the linear applications here, and then we'll spam. Oh, that's a lot of emails, Ryan. But no, but yeah, we'll go through. We'll get through our linear applications, and so all these first like labs for op amps will be all like the linear op amp circuits, if you will, and then we'll go into the next chapter 36 and start looking at some of the non-linear applications, if you will, and then we'll have labs for those as well. All right. I am going to stop recording.